Good day, everybody. This is the data capture and data processing session of the imaging and metrology track of Oceanology International 2020. My name is Walter Jardine. I'm BP's Survey and Positioning Authority. I'm one of the co-chairs for this session, and my co-chair, Daryl, will just introduce himself now. Daryl?
Hi, I'm Daryl Newborough, and I'm the Technical Director of Sonodyne.
So we'll be helping you through the next four sessions, four presentations that we're going to be providing. The first of those is from Eric Primo. Eric is actually a colleague of mine. He works at BP as a senior technical specialist. Eric graduated from Plymouth and Heriot-Watt universities in marine civil engineering and hydrographic surveying, and also subsea engineering. He's been in the field as a surveyor, offshore manager and consultant on site investigation, inspection and engineering projects. And then onshore, Eric has worked for a number of contractors in project management and business development. But in 2011, he joined BP as a geomatics manager in the Caspian Sea and then subsequently the North Sea. In 2019, Eric was appointed Senior Technology Specialist within BP to drive technology developments within the global subsea execution function. Eric is a fellow of the Chartered Institute of Civil Engineering Surveyors and a chartered engineer. So I'm going to hand over to Eric, and he's going to present his material to you now. Over to you, Eric.
That's great. Thanks a lot, Walter. If you can hear me.
Candid, indeed, yep.
Okay, well, I'll share my presentation and thank you very much. Thank you very much for inviting me to speak at Oceanology International 2020 under the data capture and processing theme. And I would like to present BP's perspective on the evolution of fast digital imaging, which we believe to be a Renaissance technology. So what is fast digital imaging? Fast digital imaging is a technique, not an inspection category. Fast digital imaging captures high quality images, stills images in place of video, synchronized with stills with high intensity pulsed lighting. Fast digital imaging can be employed in conjunction with field gradient CP systems. The point being field gradient is it's non-contact, so you don't have to stop the inspection program. Fast digital imaging can acquire data at up to 8 kilometers an hour. Data is acquired in a single pass, processed and reviewed after the acquisition cycle. Fast digital imaging may be configured for general visual inspection, referred to as GVI, or fast GVI, fast general visual inspection, by adjusting sensor configuration and geometry. Fast digital imaging is ideally suited for fast ROVs, AUVs, work ROVs, or remotely operated combination unmanned surface vessels and underwater vehicle systems, which is certainly the perceived future direction. And fast digital imaging, because of the nature of the products, the data that's acquired, is ideally suited for automated event and anomaly identification and classification. So within BP, and I think within the industry in general, there's 5 inspection categories: pipelines, jackets, risers, and hardware. And each of those has a component that may be requiring horizontal or vertical inspection, and also within operations within 500 meter zones. And obviously all water depths from the beach to the deepest asset. So fast GVI is roughly an external assessment for gross risk to the asset, whatever that asset might be. Whereas GVI, a general visual inspection from a pipeline perspective, requires a much greater circumferential visibility of the pipeline or the structural member, and potentially a cathodic protection or a monitoring of the level of cathodic protection that's afforded to the asset by the protection system, whatever that might be, anodes or impressed current. And fast digital imaging has become BP's preferred method for performing underwater asset inspection. So BP now has a specification that outlines the minimum requirements for fast GVI and GVI, and they're quoted in o'clock positions rather than coverage. Fast GVI requires a minimum of 9:30 to 2:30 o'clock coverage. That essentially means about the top 160 to 170 degrees of the pipeline plus seabed either side. GVI requires a greater degree of circumferential visibility, 8 o'clock to 4 o'clock is quoted in the documentation now, but also sufficient overlap information to create three-dimensional models, either points cloud or surface models. And again, the pipeline either side, the seabed either side. So BP has now a track record of performing 6 fast digital imaging campaigns globally, and globally meaning North Sea, Trinidad, and Azerbaijan, Georgia, and Turkey, or the Caspian region, with varying degrees of coverage and speed acquired. And we see the still evolving solution between the type of data that we require, the sensors that we need to acquire that data, how we mount those sensors on the underwater vehicles, and potentially how we operate the underwater vehicles from vessels, surface vessels, manned or unmanned. And this is where a lot of remote operations comes into the equation. Fast digital imaging delivers quality products that we are trying to, through continued use, standardize and normalize within the industry. And BP now is certainly not the only company that's using fast digital imaging as a data acquisition methodology. Effectively, we're aiming to set a new norm for inspection, moving away from videos, contact CP, and much slower, laborious data acquisition methodologies. So fast digital imaging also impacts BP's vision within the low carbon agenda. Within the 6 campaigns conducted to date, 62 vessel days have been saved employing fast digital imaging technology. That equates on a very average 12 cubes per day to 789 cubes of diesel saved, which equates to 2,052 tons of carbon dioxide not released into the atmosphere. Additionally, the saving of vessel days equates to approximately $8.13 million saved in direct vessel utilization. And there's current opportunities to grow these savings through integration with unmanned surface vessels and underwater technology, integrated underwater vehicle technology, and the whole sphere of remote operations. So a quick outline now of the types of inspection that we require, fast GVI in this case, and the type of history that we've got. So this is largely, it's not to scale, but the baseline between the port and starboard acoustic sensors is about 90 centimeters, less than a meter. So one of the challenges we have with an acoustic system, or not acoustic system, one of the benefits of an acoustic system is that we can see the pipeline. You don't need to have a viewpoint from 2 perspectives. So the acoustic coverage with a pretty minimal baseline and a low flying altitude is still fairly good with an acoustic multi-beam system. About 220 degrees. You can pick up your 5-point files, as you can see, quite adequately using that technology. Photogrammetry, i.e. with the stereoscopic images, if the cameras are placed in the same location, actually can only yield a far smaller field of vision, a model. And the reason for this is because you can only see or model what both cameras can see. So if you just take the rough perspective of the port and starboard cameras there, you can actually see by the dotted lines that there's a minimal area of overlap of both cameras. Stills imagery, also taken from a single perspective, i.e. in this case the starboard camera, is distorted and offset from the model. So although we can get great results with this lower, shorter baseline between our sensors and a low flying altitude, there are some drawbacks to it. However, overall, this may suit the needs of an operator, an asset owner's requirements. And as you can see, the distorted geotiff. So if we now look at how we can improve that, which is now, instead of a stereo, we've got a triple camera perspective. So we've got the same acoustic coverage, same 5-point files, but this time, if we put a center camera in it, we've actually got much greater photogrammetric cover. So we have a triple camera, and you can see the field of view, the overlap between the images is greater using triple camera. It's in the order of about 170 degrees. And again, the motto here is you can only see what you can see. The stills mosaic and imagery mosaic for the 2D geotiff, basically the plan view, is now a lot more symmetrical, meaning there's far less distortion, and the overlap is significantly improved to give you a much wider corridor of visibility. What the challenge we still have with this rather short baseline, this approximately less than 1 meter baseline, is actually looking underneath the pipe to see what happens in the transition zone between the seabed and the pipeline, as indicated by the red circles. So the way we improve our visibility here is to bear with me, is to broaden the baseline to what we have determined through experience of being about 2.5 meters. We've still got the triple camera perspective. The multi-beam coverage is adequate, but with the larger perspective, we get slightly more photogrammetric coverage for derivation of photogrammetric extracted points clouds or surfaces. We also used pulse lasers and lighting at the outer camera locations to get more coverage in this area. And we have a stills synced forward camera. And a lot of this is to do with providing the pilot information, because now the pilot is not navigating through video, because potentially they could be above the pipeline, they could be out of visibility. But in addition to that, we're actually looking at how we're going to move this technology into unmanned and remotely operated systems. And this here is a schematic of the actual setup that we utilize for our inspection. And you can see that the outer port and starboard cameras are actually tilted inwards. There's one other scenario which actually has not made any industry ground at the moment, but we're looking at for very good reasons, and that is to have a 5-camera dual port and dual starboard perspective, which actually removes the need for lasers. So the port camera gives you an adequate port stereoscopic visibility. The dual starboard camera gives you good starboard photogrammetric coverage. And with the center camera, you get a great 2D overlap for creating your overall geotiff. So this geometry really is providing us everything we need, the full coverage, which allows us also to go full velocity through the inspection cycle. And again, a synced stills forward camera. These are some images of the configurations that BP has employed in various regions, fast ROVs, work-class ROVs, to actually perform the inspections, fast digital imaging inspections, which have been tremendously successful over the last 3 years and 6 campaigns. What we have here is a classic 3-camera perspective. In the background, hopefully you can understand the model. The surface, which is actually in this case a points cloud, is presented with the port center starboard stills cameras, with each of the images within those stills cameras kind of pictured in the frame. And you can see the tilting of the port and starboard required to actually create the model. And the deliverables are in a single deliverable format that is accessible within the BP corporate data store, but also allows interface through the user to gather the data and look closer at events and anomalies that's required. And the detail, this is an extracted points cloud model, is actually phenomenal. Very high resolution, high quality data. and the 2D georeferenced ortho mosaics are very highly resolute as well, probably more highly resolute that I'm actually presenting on the screen. And as you can see, just zooming into a starfish in this occasion, if that was a bit of damage or debris, as well as the fact that you could see potential scarring, anchor scarring, or dropped objects or anything else parallel to the pipe ordnance rocks, it's easily identifiable and easily accessible and viewable within almost anybody's corporate data store. We have moved this on to structural inspection as well. Now, again, we have a three-dimensional model in the background, and each of those green dots represents an image. And unfortunately, it is low resolution because it's a pretty poor screen capture, but you can see the principle is the same, but that's for a vertical inspection. And for vertical inspections, we're actually looking at techniques such as visual SAM, visual simultaneous localization and mapping, and actually structure from motion, because the relative precision between cameras is not derived necessarily through positioning. That might be the first iteration, but it's actually defined by identifying common points within each image.
Okay, a couple of minutes, Eric. A couple of minutes.
Thank you, Walter. Primary takeaway messages then. Fast digital imaging is BP's preferred technique for inspection, and that's all categories of inspection. Fast digital imaging is a data-focused Renaissance technology. Data-focused meaning it meets the requirements through detailed discussions of the integrity engineers and asset owners. Fast digital imaging delivers products compatible with BP and, I suggest, other operators' data, corporate data stores. And in BP's case, this is the OneMap environment. And fast digital imaging and USV, unmanned surface vessel systems, lower the carbon footprint, lower risk by removing persons from the field. And ultimately, BP will review and implement advanced and alternative techniques, inspection techniques, to further increase inspection efficiency. Thank you very much. Time for questions.
Excellent, Eric. Thanks very much. Very slick and good timing. Daryl, I don't know if you do you want to kick things off? Have you got some questions? I've got a few myself, but maybe you want to have a stab, and we have our other presenters on that may have a question or two. So we're going to open up to the floor, and maybe we'll start with Daryl and see what he has to offer.
Yeah, so Eric, yeah, very good presentation and very interesting. I'm interested on the lighting side, because you've shown some fantastic images. This is strobe lighting. Is there any challenges there with providing that lighting? And then also probably discuss the benefits and disadvantages of using lasers over additional cameras, and that in association with the lighting.
Yeah, great questions, both of them. And you're right, I touched on them, but I certainly didn't give them adequate time through that discussion. Lighting is absolutely critical, and that's why it has to be synchronized. So every image has a synchronized pulsed high intensity strobe lighting. I don't know what the actual lux intensity is of the light, but it is adequate. And that is actually what delivers, not just having a high resolution camera. You really have to get that lighting at the same time pulsed. And the challenge with the lighting, the reason it has to be synchronized is because the lighting is actually relative to the perspective of the camera that's being used. For example, if you've got out of sync, you flashed on maybe the starboard and the camera took on the port, you'd end up creating a whole shadowing effect and significantly degrade the image. So lighting is key, absolutely key. And actually, unfortunately, the pulsed lighting gives you a higher burst of high intensity lighting than continual lighting. So it's much more efficient to burst it. The laser is fantastic. Laser data is great, especially if you actually use, I don't know, a time of flight laser, or more the type of laser where we actually slice through an image. The data resolution of that laser data is great. The challenge is that it's actually sometimes too great for our need. And all we're actually looking for, we're not doing an outer straightness here or an ovality check. We just need high quality imagery that we can create high quality models from. So that's why the proposal for this kind of 5-camera dual port, dual starboard and mono center is actually so interesting. because it's the only way of getting increased circumferential visibility and coverage around a circular asset without using lasers, because of the classic problems of photogrammetric techniques needing to view the same point from two perspectives to render it.
Okay, I just have one more question and then I'll to Walter.
Sure.
One of the key things is that the size. You're having to increase the aperture. This presents challenges. Obviously, that the width of your aperture is proportional to the height above the flight that you want to fly at. And if you're doing 8 kilometers, so around 2 meters per second, that's what's your imaging rate, and what are the challenges with trying to fly at lowish altitudes to get the coverage, but high enough to be safe for operational?
Yeah, again, all really good questions with an understanding of the geometry and the configuration that's required. And also, it is a function of altitude and velocity. All of these things come into it. And really, you're kind of looking for a sweet spot in all of that. You do have to ensure that you have adequate overlap coverage, not just across with the 3 images, but along track as well. It is critical. We're generally aiming for about 3 frames per second per camera. That's kind of the approximate image density that we're acquiring. Now, talking about the geometry, the 2.4 meters, this is what we've identified as being optimum. How you get to that geometry is another really interesting question. At the moment, we tend to use fixed geometry, i.e. rigidly mounted sensors. As we get into electrification of manipulators and booms, you get a lot higher quality control and feedback from the information, i.e. where is the end of that camera in XYZ, pitch, roll, and orientation as well, to redefine dynamically the origin of the image. That is not developed yet. It's under discussion and it's under review, but that is how we see being able to move forward.
Okay, thank you.
Thanks, Eric. Yeah, we're almost out of time, but I've got a couple of quick questions. I've got more than that, but I'll restrict myself. An interesting slide at the beginning showing the track record that we've started to build up at BP, or you've built at BP. I was interested in your view on what are the main factors that impact the average rates that you're achieving. I mean, clearly that's a key factor here. The idea here is to save vessel time and reduce costs and improve safety and the HSE footprint and carbon footprint. So there seemed to be some kind of correlation between the number of kilometers that you have logged to do, broadly speaking, and the speed you can achieve. So is that the main factor? If you've got more pipeline kilometers to do, can you pick the rate up and how complex the surveys are? Or is it more to do with the platform that you have the system on, because that varied as well? I saw a little bit of info on that would be interesting, Eric.
Yeah, that again, all really good questions. Absolutely. If you've got a major trunk line, hundreds of kilometers long, and you can just keep going down that line. And again, the whole point is that you don't stop the inspection. There is no contact CP required. You're using field gradient where a CP assessment is required as part of the survey, as opposed to doing lots of smaller, maybe 300-500 meter or minimal, just a couple of kilometers, because actually the inspection cycle takes less than the setup and the get on the pipe, get off the pipe, calibrate, check your systems. Is it all working? That can take as long as the actual inspection itself. So that's actually the real challenge. It's far more suited for much larger trunk line inspections. I say at the moment, bearing in mind that we're still talking pipelines, refining this technique for all 5 inspection categories. And if you can imagine going up risers and getting that single run, going into a hull inspection for a FIPSO, or a hardware, a manifold, or a well inspection. Now, they all take different techniques and different setup times and different acquisition times, but certainly the digital imaging technique, where each time you're creating models that lend themselves to year-on-year trend analysis, because you can check one model against another year after year. I mean, there's so many advantages to the output data format over video that lends itself to automation of the inspection reporting criteria for all classes of inspection.
Great, thanks. I think we better leave it at that. So I apologies, we sort of run out of time for any additional questions. But I'm going to hand over now to Daryl, who I think is going to introduce our next speaker. But thank you, Eric. Excellent.
Okay, thanks.
Yes, so our next speaker is Manuel on cloud-based AI video library. So Manuel Parente is the CEO of Abyssal. Manuel started developing software from an early age and has been involved in software engineering ever since. He has over 14 years of experience running and managing startup companies. Manuel has experience in developing solutions for subsea operations. His software solutions are used by most of the top oil and gas companies worldwide. At Abyssal, Manuel is the founder, CTO, and inventor, holding a patent portfolio in augmented reality, deep learning, and remotely operated vehicles. So I'll hand you over to Manuel. Are you muted, Manuel?
Now I should be fine. Can you hear me fine? Can you hear me now?
We can hear you. Yep.
Oh, all right. That's fine. So thank you for having me. So what I would like to talk about today is a digital platform and how that enables a video library that receives essentially telemetry from live operations, and how we use that to perform AI processing in a cloud-based formation. But I will give you a really quick general overview of what that digital platform is, but I'll focus much more on the AI and give you several examples of what we've done with models in AI and in real use case scenario. So the presentation will be on how we can design, simulate, and plan an operation. Essentially is how we can take real world information and translate that into a 3D GIS world, so a digital world, and then talk just a little bit on how we execute the operations and capture the data from offshore. And especially I'll be focusing much more on how we process that data with AI, and how the result from those AI models are be contextualized in the 3D world again, keeping you that digital field always updated. Just a quick overview is the main three components that I'll talk about is the cloud, which is the main system where our users use to manage offshore operations, live or otherwise. The simulator is how we take that real world data and use a physics engine to simulate operations and do virtual system integration testing on top of that data. And then the offshore is the offshore component that we install in the ROV control room. Much more focused on is how we do automatic integrity threat detection in pipeline inspections, and 3D volumetric reconstruction based on legacy video, and then metadata extraction from video analytics. Essentially, in the design stage, this is where our clients and users log in and have their capabilities of creating that digital field. I'll give you a few examples of project setup, creating the field in 3D. So basically, we take information from multiple sources like 3D data, survey information, engineering analysis, and we create that digital version from those sources or data, including point clouds and laser scans. Also, this is used for virtual system integration testing. So moving a little bit on, so this is how now we have a digital 3D version with GIS capabilities very accurately. Now we can move on into the simulation component. This is where we plan operations before even going offshore. We're using a physics engine, and based on that GIS and CAD data, and also data that we extract from the AI components. When we go into execution, this is where the operation actually takes place. We have a kit that's installed near the ROV control room. This is where we do most of our operation management, but also that's where we correlate video and data sources with the telemetry. That's later on. Those kits are sending information via satellites to our cloud, and inside that cloud, the data is being correlated together, and this is where the AI comes in. So offshore, the kit offshore has this kind of feeling because we know where all the 3D information is. We can also create augmented reality for the pilots. This is the real world with a digital twin on top of the video live for the pilot. So even if he has zero visibility, we're able to visualize and navigate, but also correlating data from other sources. This is an example of telemetry from an asset live while the ROV is operating. There's just a few examples of that in operation. So the capture process is, yes. So we're doing the operation live offshore. How can we extract data that's already on the cloud? For us, it is a use case of how we use the cloud system to create command centers for our customers. This is an example in BP. This is where we were monitoring an unmanned surface vessel that was also deployed an ROV, and we were tasked with monitoring all of this operation. So moving on to the processing component and subsea artificial intelligence. So what we created was a subsea.ai platform. This is going to be a marketplace for machine learning models and annotated data. So it's also going to be a faster data annotation platform. And why? And that's because we need well annotated data and lots of it. And the main and building those models is challenging. So we're going to allow our users to be able to access those models, but also the critical component that the bottleneck of creating AI models is labeling and annotating data. So we created ways of making that much faster, actually 80% faster in training AI data. So this is how we do it in that subsea. I'll give you lots of examples after these slides, but we essentially collect the data by post-process. We can take legacy videos from our customers, so essentially terabytes of videos, and we then create tools for our users to annotate. So essentially to create all sorts of different models. And then we help our users train the model and contextualize the result in a 3D environment. That could be volumetric reconstruction, which I'll show you. So these are the examples that we've done in the past in all sorts of situations. One example is automatic integrity threat detection. In this case, we are detecting with 98% model accuracy integrity threats in a pipeline inspection. So we're saying, is there or isn't there an integrity threat in this image? But we're also segmenting with 98% model accuracy where that asset integrity is. So green is bad, red is good. You'll see the coating on that pipeline as an integrity threat. Other examples is purely video analytics, so extracting metadata from each frame. What we do is we take in a year worth of operation and we geotag automatically. We analyze the video overlay and we geotag automatically and contextualize each frame with queryable data. So essentially you can find every video clip in which a specific asset appeared on screen on the last year. Another example is, as I normally say, is understanding stuff on screen. And we create models to do that. So if we have a year worth of operation, we need to understand what we're seeing automatically. An example is finding subsea structures, ROV arms, so that we can take out when we're doing volumetric reconstruction. understanding if there's a sacrificial anode or not, text on labels, biofouling, and fish. We specifically took on the challenge of creating AI models in which we could identify fish on screen, because it's a hard thing to do. Finding a yellow structure in a black background is easy. Finding fish with all different shapes and sizes, it's difficult, and that helps moving the technology further on. So in this example, this is going to be you against an AI that finds fish on screen on the top side, and the AI will begin searching for fish and will give you a probability cloud when it has a statistically high probability of being a fish. It already found a fish. So in this case, I'll move a little bit forward. So there's a fish there. Obviously, this is a biased and just interesting situation. Normally, the AI will find a fish as fast as a human, but this is important in the next slides. This is also important in an aquaculture setting. Say again, Daryl?
5 minutes.
That's fine. Thank you. So moving on to volumetric reconstruction, we created an AI model that uses legacy videos and reconstructs in a point cloud and with an accuracy of 1/2 inch. That means that we take a year worth of operation and we volumetrically reconstruct what we're seeing independently of the camera or video quality, and not using stereoscopic cameras. That allows us to, and this is an example from a real world case that we've done for a customer. So they had a pipeline walking issue and essentially a plat movement issue during 4 years. So they had, the first year they had video, the second and third they had laser scans, and the fourth year they had video again. And we were tasked with identifying the movement of that plat throughout the years. What we've done was to volumetrically reconstruct the first and the fourth year, and put them contextualized in that 3D environment, geo-contextualized, meaning that, so this wellhead here, if you can see my mouse, this wellhead here is the same wellhead. Sorry, this plat head here is the same as this plat head with a 4-year difference. So this is how much it moved throughout those years, and that was correlated with, that was validated with laser scans later on, that accuracy. Obviously, with volumetric reconstruction and pipeline inspection, we do automatic free span reconstruction and identification, not only based on video recognition, but also with telemetry. The real world example, another real world example of multiple models combined is this. We were tasked with only having this video. So the real footage is the only data that we had. So with this data, we volumetrically reconstructed what we're seeing, and on top of it, what you're seeing is the point cloud reconstructed, but on top of the original CAD model. The difference between what we're seeing in the point cloud and the CAD model is the thickness of the marine growth. So we were able to automatically reconstruct and analyze the marine growth in this imagery. At the same time, we're also able to estimate the position of camera movement based on video, so that we could estimate the position of the ROV within 1/2 foot of accuracy, because beneath the spar there's no positioning available. Nor we did analysis on this metadata. So the result is the reconstruction of everything we saw, and the reconstruction of the operation itself. Another example is, let me see if I can move the slides here. So with all of this information combined, there's lots of things we can do by combining the different machine learning models. So we can take a year worth of video, reconstruct the scene, but also identifying each different component and categorize those components. And then by using other machine learning models like automatic status identification of anodes, we can identify every anode that's under a certain threshold on a specific field by using legacy data, along with much more other applications. So this is about it. I'm open for questions.
Well, thank you. That was an excellent visual presentation of yeah, look, really quite interesting. I'll let Walter start with questions this time, as I hogged it last time.
That's okay. Yeah, thanks, Daryl. Yeah, really interesting, Manuel. Some fantastic imagery there, and I think certainly this is the way the industry needs to be going. You know, fabulous. I guess I have a survey background, so I guess my interest is very focused on the spatial aspects. Now, clearly, you're integrating large volumes of quite disparate types of data. You mentioned legacy video data that may have legacy positioning systems on board that may or may not be great. You presumably are integrating 3D laser scans from structures done in the fab yard. You've got as-built data to try and tie in, which will be subject to errors depending on the water depth and the positioning systems used, etc. And unless you integrate all of those systems accurately, then you're going to result. There's a danger that the results are not valid for volumetrics, for distances or changes in between periods of time where the systems you've used to collect the data has varied. How do you manage all that? You also talked about global context or world context and local context. How do you achieve the spatial integrity of all of those different types of data so that you get accurate results?
So thank you for that question. We use a statistical approach. Our point is that, well, first of all, from my experience, and if you compare two sources of data from the same asset or the same field, it never matches up. That's something that we always assume. But when you have two pieces of information about the same thing, you have a statistically more accurate representation of that situation. And this is where we, if we're using a laser scan and we have survey information and we place them one on top of the other, we gain information just by contextualizing both of that sources of data. So we take a statistical approach. The more information we have from different sources about the same thing, the more accurate and statistically accurate and more confidence we have on that data.
Okay, so you're using kind of a statistical approach, yeah? And is this all in, largely, are you working in relative space, relative to one another, or do you also work in the real world with real world coordinates using coordinate reference systems, or is it largely in relative space, you know, where you map things relative to each other? Do you have a format for how you work, or a way that you work in that respect, please?
Absolutely. So a great question. So it's always in georeferenced mode that we work. We never work local in local differential coordinates. It's always real world coordinates.
Okay.
And the system where we contextualize the result from AI, it's a GIS system with 3D. So even the volumetric reconstruction is GIS accurate.
Okay, yeah, that's it's not a phrase I've heard before, and we could talk for hours about that, but a great answer, thank you. So, I mean, I think I'll hand over to, well, I think Eric, well, let's go back to Daryl. You're running this one, so I'll leave that to you, but it looks like Eric might have a question, but back to Daryl.
I'll open up to Eric, please.
But thank you for that. Great presentation. Just thinking about the kind of use of the model, the digital twin that you're talking about with respect to unmanned and remotely operated systems, where maybe you're operating an underwater vehicle, maybe from a surface vessel, but there's a latency, a delay in all of the reaction time. How would you see your models providing benefit or any input into that kind of environment?
Well, we had situations where we had to use AI in real time. So you have to make you have to dial out the accuracy when you move on to real time situations. And it also depends on the problem that's at hand. If you're looking into unmanned semi-autonomous vehicles, then the need to volumetric reconstruct the need may be less accurate than we want for survey information from live survey. We can do two things: use a less accurate model for live control and live semi-autonomy of the vehicle, and keep the raw video file so that we can later on in post-process have a more accurate reconstruction from the vehicle.
Okay.
So you can dial according to the situation.
Okay, that probably nearly brings us to the time limit, but just have one final last question, which is you're doing some real-time anomaly detection. Is that actually on the vehicle so we can deploy that onto an AUV? And if it detects an anomaly, it can go back and do a more detailed survey of that area, maybe a visual from a multi-beam or.
Absolutely. So, but in all fairness to the current status of the technology, the volumetric reconstruction with half an inch of accuracy takes two frames for each frame you're processing. So that there's no possibility yet of doing that in real time. So it has to be in post-process. But there are certain situations and models that can run on an edge computing system on the vehicle itself. So I don't consider that those the same models as you use in post-process. So models for edge computing are slightly different, and they have to compute and treat data slightly different because the circumstances is speed and not accuracy.
And you don't have all the data by that point, so you can't go forward back. Yeah. Okay. Okay, so I think that concludes that one. So over back to you, Walt, to introduce the next presenter.
Yeah, thank you, Daryl. This is all going very well so far. So I'm going to introduce Gauthier Dreyfus, who's the CEO of 4C Robotics. So Gauthier is a petroleum engineer by background, and he has 5 years experience in the oil and gas industry. Prior to founding 4C, he worked for 2 years as a field engineer, both onshore and offshore in Africa. He has also worked for Schlumberger Business Consulting as an analyst for North Sea projects. He graduated from the École Polytechnique in France and the IFP school also in France, but also from the Texas A&M University in the USA. And I guess, Gauthier, that makes you an Aggie, I believe. So Gauthier is going to he's going to talk to us about agile metrology from a PSV, which I'm hoping is a platform supply vessel abbreviation. So over to you, Gauthier.
Thanks for the introduction, and thanks for the excellent presentation we had so far. Can you just confirm you hear me well and you see my screen?
Yeah, you're good.
Excellent. Agile metrology is a concept we developed in collaboration with other partners, and one of them is GeoFit, which is a French photogrammetry company. Unfortunately, they couldn't make it for today, so I'm not a photogrammetry expert, but I will try to go through the presentation alone. So just the context, of course, you all know metrology and the need for precise measurements between two structures. So usually what you wanna measure is distances, heading, and relative angles. So it's relative between one structure to another, and accuracy is really key. So the concept we developed so far really started from technologies together and technology breaks together. So the first of them is realizing that new LBL network made huge progress, and the rise of sparse LBL is bringing nice solutions to the market because it means you can have the same accuracy with less sensors. Then 4C, we bring the Atoll ROV, which is a smart tool that can deploy LBL frames on the seabed from very light opportunity vessels. And this is something I will introduce. And then also have several photogrammetry techniques that have been improved, and for sure BP and Abyssal also introduce new photogrammetry techniques and new imaging systems. So what I'm going to present today is not just about one company. It's just a concept that you can bring together with several techniques. So it can be any LBL sensor, any imaging techniques, and of course any ROV. But today we do this presentation and concept with 3 French companies. So IX Blue, which is a market leader in IMS and acoustic companies, in acoustic systems, sorry. Geofit, which is a French expert in metrology. And they have a huge track record with some of the majors EPC in the world. And 4C, maybe a quick word about 4C. We are a young French company created 4 years ago, and we develop smart hardware for offshore industries. And we basically focus on repeatable tasks. So we develop ROVs and vision systems for automatize any repeatable tasks in the industry. And one of these repeatable tasks is acoustic sensors deployment. So it all started observation and actually French big major realizing that most of the time the constant vessel deploying acoustic beacons, and constant vessel can 100K a day rather than PSVs are everywhere on the fields, and the cost is usually less than 10K a day. So clearly there is a need to shift some operations from big constant vessels to lighter vessels, which are on field, and most of the times the PSVs, the farm supply vessels, are not used, less than 60-70% use rate. And why would you use a 400-ton crane to deploy a 10 or 20 kilograms beacon? So this was really the first operation, and this is why we started to push this Atoll concept and what kind of tool can we create to deploy an LBL network on the seabed. And the concept I'm presenting here is using the by 4C that could be deployed from a PSV. And the first step of the concept would be to deploy a few frames on the seabed, usually 3, and then perform the photogrammetry treatment or the imaging acquisition from the same ROV. And because the ROV has autonomous capabilities, you can imagine a pre-programmed flying path and make the acquisition autonomous. So this is a concept. I was supposed to present that last February before the COVID started, and we were supposed to organize offshore deployment in the summer. Unfortunately, everything was kind of standby. So I'm still presenting the concept, but I don't have any real data to show you today, unfortunately. So a quick word about the Atoll vehicle. Atoll is a project we started 2 years or 3 years ago in collaboration with Total. So Atoll is a smart ROV that can be deployed from any vessel. So you can see a very light survey vessel. Of course, this would be shallow water here, but you can see the vehicle deploying an LBL frame up to 100-meter water depths. So this was the first trial with the first vehicle design we performed. And this is a trial from last year, still with Total, slightly bigger vessel, DP1 vessel, and we can reach now deep water depths, approximately 1,000-meter water depths. So the vehicle has its own launch and recovery system. The design has slightly evolved. So let's say the Atoll ROV is an ops class ROV with a hook. It's like a motorized hook and navigation capabilities. And we with us have, of course, a very precise positioning. Positioning is key. So we were using at the time IX Blue gaps. Of course, we are totally agnostic in terms of sensors. We can use any acoustic device from Sonar in our Kongsberg, for instance. And we also perform the boxing with the frames. So just a screenshot of the vessel GPS. So the first part of my presentation is very visual, but it's just to show you what kind of tool we are deploying in a very operational context. We also developed a latching system, a remotely controlled latching system that can be very helpful to deploy and recover friendly. INS DVL, so the vehicle itself is survey graded, and positioning of the vehicle is very important when it comes to photogrammetry acquisition. And we also have this photogrammetry camera with all the offsets between the ROV reference point and camera controlled by dimensional control. It's just a quick view of the latching system. So we can mount a latching bullet on the top of the frame or even on the top of the beacon. Then we use our visual docking technique using QR codes for precise autonomous docking, and we can grab and release the LBA frames. So that's for the Atoll tool developed by 4C. And then we started to work with Geofit, this French renowned photogrammetry company. So you're probably more expert than I am in photogrammetry techniques, but basically photogrammetry is the art of creating measures from pictures. And what you need is a camera movement, because you need like the presentation from BP explained, you need you need to see the same point from different images. So these are images from Geofit campaigns. When it comes to photogrammetry, it's key that you reconstruct your scale with the right tools. So one of these tools is to you can scale bar inside of the image, and then you use the scaling information to adjust your positions. And the other technique, of course, is to use acoustic, but now with the improvements of the SLAM techniques like visual and inertial navigation, probably some of you are already working on using the INS information to rescale the imaging acquisition. These are some images of the Geofit processing, so I won't have much comments. Unfortunately, my colleague couldn't join today. But basically, the Geofit developed a software where they recognize point of interest, and they can reconstruct 3D images using cross images. So processing is very fast. I know Geofit also try to put 3D models onto 3D reconstructions. So this is something that can be very helpful as well to rescale your images. So it's all about photogrammetric scaling, like I said. So this is why when it comes to metrology, and usually you expect a centimeter error and maybe 0.1 to 0.5 degree error. So clearly scaling is key. And this is why clients would deploy LBL networks, because as far as I know, it is the only 100% certain way today and accepted way by operators to perform metrologies. I know some visual sensors are coming on the market, combination of vision and lasers that can perform metrologies. But let's say 80% or 90% of the metrologies today on the market are using LBL because it's a very high TRL, and clients usually have trust in such systems. So the track record of Geofit, once again, I'm not the best person to comment, but let's say they have a very long track record for the past 10 years in the North Sea. They've worked a lot with Subsea 7, so they did some flange metrologies, flange photogrammetry, sorry, several metrologies, spool to spool and jumper to jumper. And they're also one of the first to use new 3D targets for even better 3D reconstruction. And the idea here is to put a 3D target inside the metrology receptacle, so you have less requirements for DIMCONs. It's only one target rather than some other metrology companies are using tens of targets on the structure. So it means less targets and less dimensional control required on yard. And I will end my presentation with a few explanations of what we did with the QR codes and where our QR codes can be combined with metrology acquisitions and positioning. So probably you know that QR codes are everywhere now in the industries, and they have started to be deployed even by Equinor on the subsea docking stations, for instance. So this is open source, and that's where it's important that any QR code that is deployed on the seabed can be used by any operator. But what we did is we added some extra dots around the QR codes. It's like every dot, each dot is a metrological target. And we added some standard dimensional control targets. And thanks to these extra dots, we reshaped all the algorithms. We packaged the algorithm and the software inside a single hardware, so we don't use any topside unit. The processing is done internally inside the camera, and everything is pre-calibrated. So we created this plug-and-play sensor, and each time a QR code is detected, we derive a very precise 6 degrees of freedom position. So we have X, Y, and Z coordinates between the camera viewport and the QR code, but also these 3 angles. And clearly the differentiator using metrology targets is the accuracy, because we have 1 millimeter and less than 120 degree accuracy with such system, while standard QR codes usually have a few centimeters and a few degrees accuracy with clearly absolutely no control of the error budget. So this camera is by itself a real-time photogrammetry system. Of course, we can't the models. It's the first layer of photogrammetry, because it can only reconstruct a known target, which is this QR code. So we did a few tests offshore for pile, for instance, pile installation with Subsea 7 last year. So we can measure the position and the inclination of a pile in real time with survey graded accuracies and real time. And also structure installation for TFMC still last year in the North Sea, and you can see the camera is synchronized with an external gyro. So we have the absolute inclinations of the camera every time, and as soon as the QR code is detected, we can measure in real time, embedded inside the vehicle, the positions of the structure. So if you consider each QR code as a metrology target, knowing that you have a very precise position between the camera and the QR code, and this is what typically the user screen would give. And of course, you can interface our sensor to any survey software such as Navipack or 4DNav, QPS, or the market leaders of survey navigation software. This positioning feedback can be used for metrologies because basically it will allow you to have fully contactless metrologies. Today, most of the metrologies use the world-class ROV that has to dock onto the structure from one structure to another, and each time it docks onto the structure, it measures the inclination of the structure. So it takes time and of course money, but you can imagine here that our Atoll ROV uses QR codes on the structures, and of course you would have performed the dimensional control of these codes on yard right before the operation. And
a couple of minutes, Gauthier.
Yeah, this is my last slide. So basically what we are working on, and once again, it's a concept. Unfortunately, we are not able to deploy the tests, but what we are working on is deploying very light LBL arrays using sparse LBL, then put QR codes on the structures. Let's say the cost of such operation is a minimum, and use a camera and INS DVL techniques to reduce the error. And this is what we would call agile metrology, combining LBL, the new techniques, latest innovation in LBL navigation, INS navigation, and visual navigation. Thanks for your time.
Gauthier, thank you. That's excellent. So we'll do the usual double act. Daryl, I don't know if you want to kick things off, if you have a question or two.
Yes, yeah, I feel this is a really sensible approach of combining visual, LBL, and DVL, INS. I think this is that provides robustness for these sort of metrology applications. One sort of a very simple question is, obviously with the QR codes, do you think that we could actually standardize on these if they're going to be part of infrastructure as you probably are aware on the Equinor, they've started to put on their UIDs, their docs, they've put QR codes. And I noticed you've added additional fiducials to try and improve the accuracy. But there's also a challenge with, so not only standardizing the IUCO codes, but also the detection algorithms for those IUCO codes when you start to have biofouling. It'd be interesting just to give us a sort of summary in that area.
Yeah, excellent questions. And basically, you have two questions in one. So the first question is, yes, of course, we are a very small company, so we don't have a huge marketing power, but clearly our ambition is to avoid the subsea structure manufacturer to implement these codes from construction and from design and construction. Worst case scenario, this is what I love to say, it costs nothing, right? It's just some painting, and they already are painting letters above the valve, so why don't they paint a few QR codes on the structure? So it costs nothing. We have seen by Abyssal, clearly it's a complementary technology when you need to have very exact position of your structure inside the GIS world, the digital world. So yes, we are pushing for that. And second question is, it's important that the QR codes remain complete or improper, and I don't think that's standardization. But clearly our technology is accuracy. And this is why we need to use additional metrology targets, because at the end of the day, if you need to use these codes for real-time metrology or real-time photogrammetry, you need millimetric and pointed degree accuracy, which you won't have with standard QR codes. Yeah. So it's a combination of the two.
I think my final question is when you sort of come on to accuracy. I noticed that the camera that you're using is a flat port. What sort of camera model is being used to ensure that you retain the accuracy for various pressure depths? And
Good question as well. So at first, we wanted to use standard QR codes and any camera on the market. Of course, that is the ideal world. But then we started to discuss with surveyors, and in order to reach a survey graded accuracy, you have an error budget, and you need to totally control every piece of the acquisition chain to get below this the hardware. And what we do is we calibrate. Flat port is better for very precise calibration for several reasons I won't explain. So we calibrate in a white room, and just an example, we have 15 calibration parameters, while the open source calibration process uses only 6 parameters. So we go very, very deep inside the calibration. And same for the algorithm. So it's like of course, it's open source to detect a QR code. You can hire an intern, and in a few weeks he will develop something. That's fair, and that's part of the game. But if you want to have a bulletproof system with survey graded accuracies, it's like 3 years of development with the best. Like we worked with the best photogrammetric experts in Europe.
Okay, thank you.
Yeah, thanks, Gauthier. I think we've done well. Just about your internet's just about held up. A couple of dropouts there. Apologies for that, but I think we've just about picked up most of what you said. I guess a couple of quick comments or a question for me. I mean, glad to hear we're moving away from photogrammetric measuring sticks. I have experience of that from over 10 years ago in the Caspian, and it was pretty painful. It worked, but we had hundreds of them down over a very long baseline, 120-meter baseline, I think, to install a jacket, and it did work, but it was pretty painful and very, very slow. So great to hear that the technology is moving on, and QR codes are helping to ease that. I mean, I guess one challenge I would have might be that, we've moved from diver metrology, with taut wires, to acoustics has ruled the roost for metrology for many, many years and been highly successful. Very few spools have not fitted because the metrology didn't work, the acoustic metrology. But and now we're moving to more remote techniques, if you like, without having to physically install LBL compacts, which I know is Darrell's business, but they're time consuming as well. And my view was well, I guess my question is, there's a challenge here from the laser scanning industry, I think is really the way I believe the industry needs to be going, because you can go down, you can do a 3D laser scan from a mobile or a static system on the seabed. You can get a full model of exactly how everything's been installed, and then you can measure whatever you like from that model, the flange face angles, the points that you need to fabricate your spool between, etc., etc. How do you see that as fitting in with the technology that you're promoting here? Because are they complementary, or are they competing?
Well, I say today everything is complementary. What you need today is sensor fusion anyway. Usually you need complementarity. And of course, there is a time between the market needs time to shift from standard acoustic metrologies to fully imaging metrologies. Of course, we haven't waited for the market to go in this direction, to work in this direction, but agile metrology, the way I presented it today, is a way to be aligned with the current market. Right. Most of the surveyors you would see on the use, I know laser metrologies are coming, and more clients are using it, but most of the surveyors and users you would discuss with wants LBL on the field. So the first step is, before you get rid of all the LBL array, is reduce the LBL array size. Then you merge with INS data, and you start to put some imaging data as well.
I think that's a fair comment. And yeah, I mean, we've become very used to the confidence we've gained from LBL over the last 20 odd years, but it is a relative exercise that we're performing with metrology, and it's going to be interesting to see how we integrate LBL, INS, video and laser techniques to get the most efficient way to deliver. So thank you for that. I think, unfortunately, we're probably out of time pretty much to take any other questions. So I'm going to hand back again to Darrell, who's going to, I believe, introduce our last speaker. Darrell?
Yes, so our final speaker is Batuhan Aktus. He'll be presenting on data-driven analysis for structural health monitoring of offshore wind turbines. Batuhan is a senior engineer at Fugro GB Marine Limited. Was awarded a PhD from Newcastle University for his work on systematic experimental approach to propeller cavitation noise. His technical expertise covers a range of disciplines, including numerical and experimental hydrodynamics, data analytics, and offshore structural monitoring. He has published over 20 peer-reviewed journals and 30 conference papers. So I hand you over to Batuhan.
Thank you very much, Darrell. Oh, sorry.
Are you okay? It did share initially. But,
yeah, just I think I have like my second screen. It's stopped. One second. Okay, can you see my screen now?
yes, I can see it.
Yeah, sorry about that. Like
that one.
Thank you very much. A case study for renewable titled Data-Driven Analysis for Structural Health Monitoring of an Offshore Wind Turbine. Today, my presentation will be structured in this slide, so I will start mentioning about the motion monitoring we carried out for an offshore wind turbine. Then we'll detail more about the, how we analyze the data, how we track the nature of the feedback into the finite element models, and how we use this data to integrate and calculate motions, and how we correspond in comparison to data, and all the foundation fixity to further analyze and into the fatigue models and also finite elements. And finally, I will move on to draw some conclusions from this study. I would like to express that all this study and case study was carried in the framework of North Star solutions, which we provided to oil and gas industry for combined effects of structural monitoring to reduce the HSE risks and combine the various data to provide one user-intuitive user interface to the operators of every kind, and aims to apply this existing technique that we used in condition monitoring of oil and gas structures to renewable sector and demonstrate cost-effective applicability via economies of scale. Of course, this way you won't need all the parts of the Fugro North Star, so a subset of the services will be applicable to renewable sector to make it more safe and economically feasible. So, in the framework of this case study, we have been asked to monitor 2 wind turbines, one of which experienced a loss of scar protection during the commissioning, and the other one was and commissioned as planned. So this actually gave us the chance to compare sets of data and how scar protection damage affected the wind turbine, compare how and we used our 6 degrees of freedom, which can measure 6 degrees of freedom motions at 10 Hertz. It is actually battery powered, so it can be deployed for a month. It just only weighs 2.4 kilograms and is a really small footprint. If you can see on the screen, they are pretty, they can just be deployed anywhere. So you can actually deploy it wherever you need you need to carry measurements to evaluate and have a better understanding of your offshore structure. For this case, we have installed one of them, call them lower level, is the 31 meter from the mud line, and another one is upper level, is 90 to collect the motion data. Once we get back the motion data, the first thing we look at is we carry out the spectral analysis, and this one out. We have our first observation was that, as you can see in this blue circle here, this is the first sway mode of the wind turbine. And we observed that while the control one, which is shown by the blue line, was at a higher frequency, the scarred one was frequency. And this is shown as, like, as you can see, the was 0.24 hertz and scarred one 0.22 hertz. Obviously, the main implication of this one is the first blade rate. So if the scar damage further deteriorates, then the first sway mode of the scarred wind turbine can further lower down, and in case when it becomes operational, it may overlap, so then it may increase the amplitude of this mode and causing potential structural damage. And this is actually, operators would always avoid suspicion about a scar damage. They avoid operating the turbine at all costs. And of course, through the response, another thing we know with other structures as well is to track that mode over the time domain to ensure that it is, as you can see here with the blue lines, is the control one, that is higher up, consistently higher up. But as you go along after the initial commissioning, you can see it becomes operational, then more fluctuations are visible. But the SCART one is again consistently the natural low down. In fact, by the time we prepared this presentation and like we did update recently, I think we have observed that some repair has been carried out to this SCART wind turbine, the control turbine, which we hope to present another conference. But again, this is actually a key indicator of your asset integrity for, and this is a very useful parameter for the analyst dynamic response to calibrate their models, and that actually feeds into the structural model. The fatigue life predictions for their model, so important for that purpose. Like analysis we can carry out with the motion measurements is we integrate to give the displacement, calculate the inclinations, provides us.
Is it possible to, you're very juddery, is it possible to turn off your video so that we can hear you a little bit better?
Yeah. So, is it? Hello?
Hello? I can still hear you.
Yeah. Should I continue? Hello?
Yes, we can still hear you and see your screen.
Yes. Okay, so an analysis we can carry out is using motion measurements to calculate the displacement and the inclination. This in turn gives us the opportunity to compare both the inclination and displacement measurements against the metron data and see how placement of the wind turbine tower changes with the overall impact of the essentially waves. And as you can see here, you can see the red dots are corresponding to the SCART wind turbine, and blue dots are corresponding to where the displacement is on the y-axis and significant wave height is in the x-axis. You can see the control wind turbine has 1.7 millimeter per meter significant height displacement, experiencing that much displacement, whilst the SCART one is experiencing 4.7 millimeter, 3 times the intact one. So this is essentially caused by the weak soil around the monopile, and we can see that the motion of the tower. So another aspect of this is the effect mid-ocean conditions on the first sway mode, as well as the consequent displacement of the tower to this natural frequency of the tower. So once the motion, once the soil around the tower is disturbed, the motion of the tower will be much more. So, and we on the previous figure, but also this has a direct impact to the natural frequency of the tower as well. Here, the control turbine, the natural frequency decreases 3.7 hertz per millimeter displacement, whilst the SCART one 0.6 hertz per millimeter displacement. This in turn actually takes us back to the power spectral density. So if the SCART wind turbines increases quicker with the ocean conditions, this in a case where like very high waves are experienced in the region, that might mean that an operational wind turbine's first blade rate come, overlap with the first sway mode, causing a fatigue damage. So another analysis we have regularly done for the other offshore structures and risers in particular is the foundation fixity, which is actually essentially the soil stiffness measured by the deflection of the tower profile. And this is essentially the sensitive idealized point of rotation of the generally closer to the mud line, and essentially when the anchor that allows more lateral motion below the belt mud line, causing fixity depth. And in this one, you can see the foundation fixity all polar axes all around the turbine. And you can see that as I mentioned, the sensor packages from scarred turbine experiences fixity depth along the 30 to 200 degrees axis, much lower of about 28.9 for the control tower, and term causes and reduced lifetime. Overall, like what this data is to update, build finite element models and calibrate them matching the as installed. This is done via matching the easiest way to do it is to match the dynamic response, the natural frequencies and mode shapes of the tower to the finite element models. This is the first approach to make. And the second way that this improves this feedback to the structural models is updating the soil model, which essentially analysis about the soil model. But having access to those can be refined to match actual condition. And one as an additional option to have for a wind farm to more, like instrument further the tower with various strain gauges and accelerometers distributed all along the structure to have a better understanding via calculating the bending moments and feeding them all into the structural model, and to enhance the understanding for the installation for a wind farm. So in return, this actually provides a possible of service life extension and additional revenue generation through the extended life. And actually this presentation, so what we are experienced from this case was motion monitoring of offshore wind turbines are cost effective because of the economies of scale. It aids the detection and diagnosis of structural integrity problems. And once, when you do structural monitoring of offshore wind turbines, you can detect your monopile foundation performance, and essentially by doing that, you can improve your simulation models and calibrate them to the as installed conditions, which will extend the service life and reduce the operational expenses via reduced maintenance. And this will in return enhance the sustainability of offshore renewable energy in our opinion. And these whole services are available through Fugro North Star solution integrated marine management system. And that brings me to the end of my presentation. I hope it wasn't so much disturbed by the internet.
Yes, thank you very much. It was at points, it's such a shame. It's an interesting topic. and really quite topical with the massive expansion of offshore wind. I'll let Walt have the first few questions. We only have about 7 minutes left, so
yeah. I have a couple of areas I'd like to explore. Batuhan, I thought you battled on well there. You were broken up a little bit, but the good news was when the video or the audio caught back up, we didn't actually lose anything. It was just a little tricky to focus in on what you were saying, but well done on getting through that. I guess my question is, you indicated, I mean, these units appear to be standalone, if you like. They have battery power for about a month. I'm assuming that means you need to physically visit the site to download the data. That to me is inefficient and you know, costly and carries risk. Have you any consideration to wiring them up to the internet or bringing the data live back via the cabling that's already there to bring the power to shore? I'm sure that's been considered. I mean, in an ideal world, presumably you could wire up a whole wind farm, and then you could actually compare and contrast all of the data from numerous turbines to see which ones were causing you trouble, to see which ones were giving you consistent results and which ones were maybe outliers, et cetera, et cetera. I mean, how are you progressing bringing this into the internet world where you can see this all on a dashboard in your office? Yeah,
you are exactly right, Walt. I think like I have to admit, this is actually like a client request. So this is like where they want a really short term, like spot on, like just you know, just point measurement. What we normally do is, of course, like we are experts in online monitoring, and we have a range of sensors, like a very compact Internet of Things. We can have them, you know, easily installable, and power over Ethernet power to just minimize the cabling required by the client. So we have a range of solutions. But in this case, what we have done is it's a really user-friendly system. So we have actually gave a really, to be honest, half an hour presentation to the clients' offshore engineers, which they were able to retrieve the data during their regular maintenance visits to the turbines, which they then send us back to quality check them. And this worked quite well, actually. That worked for them throughout the time when they have applied the repairs to the wind turbine foundation, and they made significant cost savings, and they made they gained significant benefit from it. But having said that, I think like obviously what we are promoting is, it is in fact should be to really reduce the operational expenditure via reduced maintenance. As you said, this should be like a you know, like a compact, connected, you know, dedicated structural monitoring that you can access and see each turbine from your desktop and see, okay, everything is looking good for wind turbine. Of course, we are also working with floating offshore wind turbines, and there's like a you know, we are currently working on some structural monitoring solutions using really minimal instrumentation, just GPS and accelerometer to derive fatigue and mooring line fatigue and structural integrity monitoring of floating offshore wind turbines as well. So that's another topic we
I mean, to me, it seems like this is almost a retrofit, and we really should be designing this kind of monitoring system into the design of the monopile itself, and then you get it all integrated to give you a common solution. And whether you use, you know, Elon Musk's Starlink system for the data, or a mesh network for our mobile technology, is probably options that you could consider. But that certainly seems to be the way this industry should be going. But I mean, it's very interesting. Thank you. Not an area I knew much about. I'll hand it back to Daryl. Maybe he has a closing question and can wrap things up. But over to you, Daryl.
Yeah. So as a closing question, there's some obviously really interesting spectral information in that PSD and a dominant direction. Have you correlated that dominant direction with current flows through the arrays, or is it more related to wave direction, or is it current? Because that will introduce scour. And also I noticed some other spectral peaks in there. Could they be correlated with like the grouting integrity of the monopile, or other integrity monitoring capability if you had a slightly wider bandwidth?
Yeah, to first of all, the question about the direction is it's definitely correlates with the Metrology data and mainly driven by the wave direction because of the location of the turbines. And definitely when you have a scarred foundation, you experience more motions and fixity depth increases. And regarding the spectral response, what we do is we do actually carry out some model analysis of various peaks that are consistent in the spectral response over time. Then we do track them over the time and try to identify the sources, as you said. So we do carry out certain further analysis to feed back to the client.
Okay, well, I'd like to firstly thank all the presenters, excellent presentations, and yeah, that pretty much concludes the data capture and processing sort of session of the imaging and metrology track. So thank you all, and goodbye.
Brilliant. Thanks, guys. Excellent.
Thank you.
Thank you all in there.
Bye-bye, everyone. Have a good day.